pointing. Okay, so let's open our project. So in the last lecture we've been working on this array implementation, and we have implemented most of the useful features, I think, already. Let's see if something's missing. So we have our iterators, we have insert menu, we have remove menu, we have some mid, we have mid. So this looks mostly complete. So now we will start with a new container type, something quite simple but also very commonly used, which is a linked list. And a linked list basically is a container type where you have the container itself has 2 pointers. It points well, there are 2 types of linked lists: singly linked lists and doubly linked lists. And with a doubly linked list, you have a container type which has 2 pointers, one pointing to the first element in the list, one pointing to the last element in the list, and each element in the list is pointing to the previous element and to the next element. So that you can start from either end and traverse the list. What you cannot do is you cannot access an element somewhere in the middle randomly, which is quite a limitation. An advantage of such a linked list, however, in comparison to an array, is that in an array, as you might remember from the last lecture when we looked, for example, on this remove or insert functions, we had to shift a lot of data around, and this effectively also meant that often we needed to run through calling the constructor and destructor on the objects which we were holding in our array, which is not always a very cheap operation. So if you would have a string of some sort, then usually you would need to reallocate all the memory, then copy the whole content and so on. So this has some overhead. Of course, if you have more advanced framework works, they would try to optimize on it using, for example, functionality that allows you to cheaply swap 2 elements with each other and do stuff like that. But this is all like it adds complexity and not little. It only works with data types that then support this mechanism. So it is useful if you have a large framework that offers a lot of data types to begin with, like the STL itself or Qt. But if you are just starting some own small framework for some custom application where you don't want to use for some reason a larger framework or the STL, for an example where this would be case would, for example, if you are developing something for a driver or if you are developing something for a microcontroller, although some microcontrollers IDs by now already offer STL support. But in case of driver development, you cannot use STL easily, and even if you use one of the hacks that make this possible, you rather shouldn't, because there is a significant risk of breaking things. The STL is very much reliant on exception handling to handle memory allocation issues and stuff like that. And in the Windows kernel, you do not have exception support. You can hack it in, but this again is something that if you value the stability of a system, you rather shouldn't do. So it's often quite interesting to write some own small framework which is optimized for your application, and then of course it's good to know such different container types and how you can make them more efficient. And for example, in many use cases you only need a list which you iterate through from one of the ends. It's not always necessary to be able to look up something by index or use more complex lookup mechanics, like to look up something by a key, which we will be, by the way, looking into it in the next in one of the next lectures to create another data type, a so-called hash table, which is rather easy to implement but gives you already quite a lot of functionality with regard to retrieving data by a key and storing them, of course. With our list that we'll implement now, I will implement you a very simple singly linked list, so it only has a pointer to the head and you can only traverse it in one direction. The homework assignment then will be to extend the list with the functionality to work in reverse, so basically by adding a second pointer. And then of course when adding or removing elements, to ensure that all the pointers gets updated correctly. Um, such a list, such a linked list is particularly useful if you have iterator support, because an iterator already allows you to kind of hold the reference to some element somewhere in the middle on the list, and then you can use this iterator to insert something at its place or remove something at its place and do things like this. While if you wouldn't have iterators, you would be only able to traverse the list two ways, and that's it. Depending, of course, on the implementation, you could make it such that that the element you get while traversing is directly the list element, and you have direct access to the previous and next pointers, so that you could, in principle, use those to insert and remove elements. But then this has the downside that it's not very modern code when you have access to more internal aspects of a container mechanism. So the approach with an iterator is technically superior than old school approaches where you just add some additional fields to your data structure and so on. So let's start. We will create a new file. Of course, we'll create it again as a template. So list. So like with the array here, we can just copy a few things from the top. Zack. Just we'll call it C list. It will be a template so that we can make it work with whatever data type we want. And let's start with our entry object. So we can maybe copy a few more things. So here, let's just grab that much. We can keep our mechanism where we use a holder object so that we can reference count it and then have easier copying. But of course the things here will be different. So we don't have size, we don't have capacity, we don't have data. Instead we will only have a pointer to the head and a pointer to the tail of the list. So and we will of course need to have some entry struct, so something that will represent one entry in the list. So with the array, since it was just an array, we could just use the type provided, but here, since we need to outside the pointers, we need some sort of type that will keep the data object plus the two additional fields. And as mentioned before, in very old school approaches, like often seen in modern Java development, you just had your structure, then you just added a member which contained the additional pointers. But this of course then has the limitation that you can only use data types for your list to list data types which have been prepared to do so. With our approach, we want to be able to keep anything we want in the list, so any type, and thus we will need this entry types. Let's call it as and it contains so it's a struct, so it's everything's kind of public in it. So it will, let's at the beginning give the two pointers per next, and there will be the second pointer previous, and this will be the to do for later. And our other one, of course, we need the data themselves. So the data, and our structure here will have the, as mentioned, two pointers, s and per head and tail, which will be a to-do. And of course the to-do will be more than just uncommented. You will need to create the mechanism to update those values. Here I just put them where they should be so that things are more straightforward. Okay, so let's start with the well, very fast operation. We need something to be able to add. Well, no, first we need a constructor, so let's quickly add one. The constructor in this case will not really need to do much or to do anything at the beginning. Then we will of course also need a destructor, and to keep in line with our design here, we can copy some of the code. So we have our attach, expand we don't need, create we will need, release that we'll need to update later on, and let's see what else we can copy. And we can maybe copy also the assignment operator, so this we will also want on our list as a feature. And we'll need a copy constructor of course as well. Oops. Let's see what else we can copy. So we can copy this and this. Oops. Zack. So the destructor just calls release, and this calls attach m. Okay, so release, we don't need to release add, but we will need to delete every entry, so this will need to be a to-do for now, because it's not as simple as the array, since we need to actually traverse the whole list to dispose of it. Create is easy. There we just let's use just a new operator. We used the malloc function before, because we wanted to have like one object that contains the data at the top plus an array of an arbitrary size, and with malloc we can allocate memory of arbitrary size. Here this is fixed size, so we just can use new, and this will be fine enough. As we said, we don't need expand. And attach just makes release and this. And what we also should do is, this is by the way something we should fix here in the array. So we actually ran into this problem before, that when we had ref count greater 1, and we modified something, that it resulted in modifying the shared data, while the intended approach here would have been to, if we see before in a operation that can modify something that the data is shared, that we then actually create our own copy and remove one reference. So we will be fixing this here in our array as well, but first here in our list, let's continue with the most important thing is, so we have our attach. This is simple enough. This release we will make later. Then we will need of course a append function that adds something to the list, although since our list has only a pointer on the head, then let's make a prepend function. Const reference value, and the append function will be a to do. Since of course one could implement a append function while having only a single linked list by traversing the list to its end and then appending an element, but this would be of course quite inefficient. So what we would of course want is when we're using an append, to use the tail pointer and then be able to directly add an element. And then we will of course need a mechanism to iterate through the whole thing, but this we'll add later. For now, let's just implement those very basic functions. So we already created the list here. What we also need to check in prepend is whether actually something has been created. So if let's make a function for that. Find prepare write, and the function will do two things. It will first check if there is no m, so if no m, then m is equals create. We don't have the capacity here. I mean, in principle, we could just drop the whole create function and just do it directly, since it's a one-liner. And else, if reference is greater 1, that's the case that we have forgotten the array. Let's go then to do it later. And then of course, if it's just 1, then everything is fine. We don't need to do anything. And here in the ref, our goal will be to then really make a deep copy of our list. Similarly to like here, we will need to go through the list for this operation to be performed. And in append, then we will just here, sorry, not append, in prepend, we will just prepare write. Every function which actually does some write access should call this prepare write, because it will ensure that we will have an m, and it will also ensure that the m we have is exclusive to ourselves, and that there is no other object which would have a reference on our m. Okay. Good. So let's continue with our prepend function. So first things first, we need to create a new entry for the data. So s entry per entry is equals new s entry. If we want the mechanism to work also for data types which don't have a constructor, a default constructor, it is useful to implement a two versions here, entry and entry, which takes const reference value t value, because this way we can handle data types which only have copy constructors or assignment operators without the need to have a default constructor. And there are some types in various cases where you cannot create an object without providing some initialization argument. This happens often enough that it's a case where we would want to care for it, and then of course we use that here. Okay, and when we have this, so the way we attach this is quite simple. So first this thingy, entry next is equals m head. So the old head becomes now the next element, and m head becomes just entry. So it's really quite simple. The things of course get a bit complicated if we have things pointing in both directions. So then it just needs some more work. And now that we have seen how this is made, we can think about how we can, for example, deallocate such an list, how we can free it. And this is quite simple. So we start with a pointer. We assign to the pointer the head value. Then make a loop. Okay, and what we basically want to do is we will just go through it. So we make a copy. Actually, we could put this, I guess, here. So we make a copy of the entry, current entry. Then we advance entry to so entry is equals entry next, and now current entry we can delete, and the thing should run as long as this is not null ptr suck. And then once we are of course done, we need to set head to nothing. In principle we could improve this and then operate directly with head without even making here a copy, so we actually can maybe add this is a small improvement. So head entry, then head is head next, delete current, and then we don't need this set null, because at some point we will run into a element where the next is null because it's the end of the list, and head automatically will already be null, so we can also make this a while loop. It's functionally the same thing. Yeah, and this is as simple as it gets. In principle, since we have two pointers, we will then of course need to clear the other one. Like set preview, not preview, or is it tail to null, m tail, just for good measure, but that's of course to do. And what we also could change here in the behavior is we could in principle make this a exposed function, and we call it clear, so that we can easily reset our list to an empty state. Okay, yeah, clear and clear, yeah. Actually we don't, oh, we forgot something. First of all, we don't need to do this because we want to get rid of m, but we definitely need to delete m, otherwise we would have a memory leak here. So and then we set this to null, of course, only if this was the last instance. So now let's see to our prepare write. So if we have the case where we have a shared element, so the data object backing our list is shared amongst multiple list objects. This can happen when we use the assignment operator or the copy constructor, etc. So here we need to now make a copy. So the mechanism will be quite similar, just that we will not be changing anything in the existing thing. Let's see, that much we can copy. So as you see, this is a destructive loop, while here we want to just read the data and not alter anything. So we need to have a copy. We can, of course, we will not be deleting anything. And since we are not deleting anything, this can be our advanced instruction, and here we'll just be working with entry. And of course we would need some new m, so as list new m is equal, or let's call it just n, is equals new list. I mean, we could even abuse the append function to do it for us, but let's do it manually. So we have our new n, and then here just okay, that this will be let me just think. This will have an unexpected behavior that okay, we cannot just use the append function, because if we would do so, well, we could use the append function, but we only have the prepend function. That was a bug. That should be the prepend function here, and this had to do because we only have the prepend function. Each time we duplicate the object, would reverse the order of the elements, which we of course would not want. So we will do it here manually. So we start at the top. We have our entry. So we will need a pointer to point to the thing. So as entry, that's a pointer on a pointer. P is equals n head reference on an head. Oops. Okay. So we make a copy, and this will be like the first thing. So the its next entry will not yet point on anything. The head, but it must point on something. Let's think about it. So what we want to do is to update the pointers correctly. So we will need to have like the previous pointer, which can be this one. That will be the head. So we just here assign p asterisk to a head, and the next pointer will be assigning then p will be equals wait, not m head, just entry, and p will be entry next reference right here. So this should work. So when we are iterating through it, the first assignment will be assigning to the head, and the second one will be assigning to the next of the previous element, and we'll repeat that until we are done. And since our s entry here has a construct, and here it's set to null, then the last entry once we do not go through the loop should be then properly assigned to null. So now we will detach the list. So we will use here this clear command. So we don't want to just decrement, because if in the meantime of us doing something, another instance would have get rid of its own reference and we only decrement, then we might end up with a memory leak. So we always, when handling with this data object and trying to replace it with another data object, we always need to go through a path where we have the option to get rid of it. So basically between this check, while we are doing this loop, that thing might have became 1, so we just here clear, and then we just set m is equals n, so we just attach it, and we also need to increment it. Let's see, didn't we forget something? Yeah, we forget something. We need to always make this incremented by 1. So let's add this here, so that we start at the value 1 and not at 0. We could of course change this so that the initial value is 1, but it's more elegant to do it this way. Okay, so this should work. This should work. The append is the to do. So of course then the next thing what we will need is an iterator of some sorts, so that we can actually test whether the list is working. But before we do that, let's quickly take a look to our array, because as mentioned we have forgot to give it the mechanism to get an additional, to make a copy of itself if you want to write something. And in case of the array, I guess an elegant option would be to go with this expand function, because although it does realloc, so this is not reliable, now we really need a new one. So let's create this prepare write, and then let's see from where we need to call it. So the assignment operator to note append of course needs prepare write, but this does already expand, so we can of course whenever we call expand make prepare write automatically. Okay, then get size is fine. Add, it's a add that gives us a const, so it's not modifiable, so this is fine. In principle we should have a second add which we have here, which gives us a non-const value. So here whatever we return might get modified, so we need to prepare write, which by the way leads us into a scenario where you might want to just get a value from a list, and then unwillingly you trigger a deep copy, because the way you got the value from the list was such that the compiler could not determine whether it will be modified or not later on. So with this path you are safe, but with this path, just to be on the safe side, we always introduce this prepare write. And for the iterators, and the approach that is often taken is that you have two types of iterators: const iterators and non-const iterators. And if you obtain a non-const iterator, then this will already trigger the creation of a full copy. In our case, one could of course extend here the functionality, so depending on which type of data pointer you are retrieving from the iterator, then it will either trigger a copy or not. But for now, let's leave it as is. The simple option would be, as said here just have a begin end const begin constant find and const find, and then just trigger the operation, the duplication. So index of course we don't need to change. Mid also don't. Insert that needs prepare write, although we kind of have discovered by append, so let's leave this as is. The other insert which only does extend is okay, also okay, because here we have a call to prepare write inside expand. Remove one does not have this, it only uses this release add. So in principle we could just put the call here, because whenever we want to release add, then we need to prepare write. Insert menu uses expand, so this is also safe. Remove menu one would here of course need to remember that to trigger this prepare write when needed. And I think this should be all the cases. So the prepare write, basically what it does is it will just make a copy of the existing data. Let's see if we can improve that. In principle we can. No, let's leave it. But yeah, right. Okay, so if we don't have anything, then this doesn't happen, but here we need it. So this is a small optimization, but still worthwhile. Yeah, and then we'll always make a copy if it has more than one reference, and then we might reallocate. We could optimize this more into just using expand for everything, actually. Okay, I think this might be an improvement. So we just expand, and for new capacity we will just say 0, because this would bug out here. Okay, let's see. And with release the same thing, just extend 0. Yeah, this is more elegant, because then we can be more efficient. So here now we change the condition from greater or equals to just refs being greater 1. Wait, so this is already large enough, and refs is 1. If it's not 1, we go here. We have our new size, we have alloc, and ideally we will just now here really make like a actual deep copy. So we'll always this will be n as array n malloc size no m. So the same as we do here in create, we can mem set everything for good measure. We can set the capacity we are already setting. Then as said, we will release, and then we will set m is equals n and increment, but we need not to forget we can use attach here. M. We could probably have used here as well. Yeah. Just attach N. Here's already part of it, so makes a nicer code. But what we are of course missing here is to copy all the elements over. So for t equals 0, size 10, e is less than m size e plus plus, and okay, so we have mem set the whole thing. And then here we also run into the complication that we have here these two different cases which we need to handle. Yeah, so if this is less than, then that we already had some shifting code which we can here grab. It will be probably more similar. Okay, let's see. Okay, with this we don't need, so this will be of course n data e from m data e, and then m data, and we call the destructor on that. And then m data n data e, m data e, and on that one is wrong. And data e is null. Okay, let's see. Yeah. This should be n. Destruct it and release. Release does release add, but since we did the destructor, so we have two options. We can here just not do the clearing. That will be done by clear. Of course, also we don't want to, because we don't want to modify the original data. Right, so here we just copy the things over, and here, okay, here we have another problem, since the way we made our array work is that if we have larger objects, we really would just work with pointers to the data, not with the data by value, which means that our expansions are much faster since we are only copying pointers around. But it also means that here we need to, now when we actually make a deep copy, this operation here will be contingent on whether it's exclusive or not. So if ref is 1, so these data we own them exclusively, then we should really set this null, otherwise it will get cleared, which we don't want by clear. Basically kind of moving the objects now. In the else case, we need to create a new object. New t from the old one, yeah. And we can make this a bit more elegant. Yeah. So in this case where we don't want to do memory allocations, we just always need to call the constructor. But if we are using pointers and it's exclusive, we can just move the pointers around, and that is really nicely fast. While in the last case here, when it wasn't exclusive, when we started, then we really need to make a deep copy, copying every element, making a new one for ourselves, and then this thing will be either disposed or not by our attach function. So this should fix the array. And now we are in our list. So there are two ways how such lists can be interacted with. One is, as already mentioned, an iterator. which is a bit more complex. And another option, which is quite simple, is to just have a function on the list which you can call, and then the function will take an argument which is a function of its own, a callback function, that will then be invoked with every entry in the list. So it's like a super simple approach. So for demonstrations, we should add this as well, even before the iterator. So so we have iPad, we have clear will be the last one. Let's add it here. Void. Let's call it enum. And this thing will then take a function pointer. Void asterisk func. Then it will take, of course, a const reference value and a void asterisk param, which is optional, which will also pass to the function itself. And here we can copy not this one, mechanism for enum. So this thing basically runs from one end through the whole thing. We forgot something. There is a typo. This has one too many semicolons. That will not work. Now we just call a function func with entry data and our param. Good. That should be like the absolute minimum that's needed to make the thing work. So let's go to main and let's add a test case for it. First, of course, we need to include that. Oops. List. Oh, we just called it list without anything, so let's call it list. Here. So list. Let's say integer. By list. It was not list, it was clist. Okay, so for int e like 0 less than 3 I plus plus list punct e append e, small e, and my list punct enum. We can use a lambda function. We don't need to use a function that lives externally, although we can only use simple lambdas without a captcha list. We can extend this later to work in a more flexible way. What was it? Int const int reference value, comma void asterisk param, which we don't care for the path, so we just null. Oops. And of course we need a body for the thing. The main idea with having such a param value is that if you implement your mechanism such that you cannot use a lambda with a captcha list, that you still can somehow communicate or to your function or make it maintain a state which is really local to what you are doing, and you are not required to use any sort of global variables or anything. So these params are very, very useful. Yeah, and cout's a new line, and you just value. Okay, let's run it. It should just print 1, 2, 3. We have some problems. Right, we have some inconsistency. We called it n, not p later on. Probably value here. this is our copying, so we want entry. We cannot use entry twice. New entry. So first of all, this should be an own type thingy, and here we will just have entry data. Okay, that might be everything. Okay, we have yeah, here a semicolon is missing. Oh, I fixed for array, broke something. Let's see. Const string other should be fine. Why isn't it? Because this is a pointer to be referenced. So you have a bug, but wait, is this really a pointer? Let's see. Data. Yeah, it's an array of pointers. Although for string, shouldn't we actually run into this case? Let's see, main size of string A. What does it tell us? 8 is pointer size. So we should be in this case, but we should not enter that case. But apparently we did. Okay, no, we didn't. It was just compiling, but we still have some issue somewhere here because our string fails to work. Wait, we didn't change anything to string. Put a breakpoint here and see the behavior, what happens, so that we can so we enter our attach, then this thing will be attach release, well, now m should have 2, which it does. That looks correct. Unfortunately, it seems it. Let's see. So we trigger the issue from here. So we have our crumbs. M size ref 0. Okay, ref 0 is not correct. Then we have a bug somewhere. Oh, I think I know what's the problem. Or not. Well, one issue is of course that it had ref set 0. That was not correct. So let's start with a breakpoint. How do we create crumbs? We create them here. So let's start at the top and see what we have. So we have m, which is already ref 0. So this is already not right. So something's in the split function. Somewhere we forget to increment something. So we create a new thingy, which should be empty for now. Yeah. Result m is 0. And then we append, and this append will at some point do something wrong. So we have a substring. It's a string, data length. is not what we're interested in. This. So we expand them. Zack. And what have we created? This ref 0. Okay, so the expand here is broken. But attach M should increase. Oh, damn it. Yeah, I should use more longer names, then such mistakes would not be that easy. We have attached the wrong thing to the wrong thing. That of course explains. Okay, that's not great, but it's at least a new error message. And let's see where this comes from. But, so it will be probably from somewhere where we create the grams array. Split. Yeah. So we go into our split. Zack. We create that thing. Length. Okay, this looks like it should be correct. We set this to 0. We go to attach the pointer. I'm going to split. Do append, you go to expand. This probably will be fine because this just creates. Wait, it creates, does create, set the create does not increment. That's a bug. Create should have here incremented our reference count. So let's fix this. Attach create. I mean, we could also copy it to p or to another pointer variable so that it's more aligned with what we are doing usually. But this just makes the code more readable. It does not change anything in the behavior. Okay, that didn't help yet. So we have another problem. Let's see. As we said, the problem was I think with split 2. Yeah, somewhere in split it is breaking. So let's this is the constructor for the other thing, so we don't care for that. Now we are here now a split. Let's see if we arrive at the end. No, we do not. So this is really broken somewhere here. Okay, step by step. Right, so we have find, then we do the append. Well, we do a few things. First with the substring, so let's see if this might be the problem. We create a thing. Then x. We create a new container with 0. This looks quite fine. Then we go into this thing, so we go into expand new capacity 1 malloc. Okay, this is fine. set capacity is new capacity, return the thing, suck. PS ref 0, okay, that is correct. After the attachment it will be 1. Okay. We've extended our array. Now we will create a new string. That should be fine. Okay, so the first iteration worked fine. The second iteration fails, so let's put a breakpoint here. So the first go through was fine. Let's see what's wrong with the second one. The substring we assume is correct. Okay, so it's most certainly the extend that will in some way cause trouble. So M is already defined. The refs is not enough. So we create a new size. I think I had somewhere code where I had extend with 0, which is not quite right. That might be a problem. Yeah. New capacity and 0 would be fine, but here we know that we have an M, so if new capacity is less than M size, then it should be just size. So that in case of 0, we just make a copy without extending it. Since we use 0 as a placeholder, so to say, for what we want to do. But that might not be the only issue. Let's see. So the first, that was already it. Okay. Okay, so we fixed what we have broken with the array. That's good. But then we run into another thing. With crumbs here. Okay, for some reason crumbs an empty string in our crumbs array, in which case we just return null, which this thing doesn't like. Let's see, why would crumbs be would crumbs contain an empty string? It should have contained 3 entries. Okay, and already the first entry is an empty string. Okay, that didn't work. Let's see. Mid. This seemed to work, and mid doesn't trigger. Wait, why did this work? That's a good question. Here. Capacity length 10. That would mean that only one entry inside of crumbs is actually corrupt, the first one. Let's, for testing here, just make it a bit more fault tolerant. So if this, then this, else we just print null. I guess we have this happening a few times. Yeah, this error repeats multiple times, so let's just copy this. There as well. Mm. Okay, that's at least a new bug. It became null completely. Okay. Interesting. So let's see when I put a breakpoint here. You didn't had any nulls now. Then we go. So crumbs in so insert broke it. Insert should have worked, but it didn't. Let's see now. Yeah, so let's see what we did wrong with insert. So insert is here. It does append, and append apparently. Well, it also does add. So append should make it exclusive already by calling extend and add. Makes append with 0, extend with 0. New capacity will be aligned to size. Well, let's put a breakpoint here and see how the thing develops. So no, that's not great, because let's run it again. Zack. So we arrive at the insert, we enter the insert. Zack, zack. Then let's see what append does. With our extend, we want to make it one larger. Then we go to get size. Okay, then we go to extend. Don't anything here. Then we just make this. We forget to copy size. That will be the problem. Where's our structure here? Yeah. Caesar underscore t u size is equals u size. So we create a new thing here, and then we need, of course, n size is equals size. Of course, need to keep the old value. We already have a u size. That's that is of course not what we want. Should have called this count and not size, then it would be more straightforward. Just rename this to ulen for now. Okay. Okay, this we repaired again. Now we are running in the error we had before. Per entry. Okay, so our we have two issues. I think I used append here in our test code. Yeah, I should have used prepend. And the other issue is that here we need to check whether m actually exists. So if no m, then return. Yeah. Um, value as and const value t from value should work with an integer. And e. So prepend. This should be of type const int reference. Here entry const int reference t value. And we can make this simpler for now. Just t is equals value sorry, not it should be data. Sure. Yeah. Okay, let's see. And it prints well in reverse order since we prepended. So this works correctly. And we have used quite a lot of time on preparing this sample and fixing the array. So I think we will just have time today to write a nice homework assignment. So there will be nothing to do today for you, I think. So we have append. Yeah, so here homework from the 11 and 7 of 11, 12 to 0 to 5.
Right, I just want to ask, I overslept big time, so I came in 50 minutes late. What exactly did we do today?
We have implemented a singly linked list as to demonstrate another container type.
Okay.
And the homework assignment will be to convert this singly linked list into a doubly linked list. So you need to uncomment the two pointers and then of course implement append, extend, prepend, and pointers update. So if we are prepending something, this will change things. The few pointers will need to be updated. Implement reverse enum. We also want a reverse enumeration function, which well enumerates from the back. Yeah, and then what we'll add later is we will add construct iterators, and then with the iterators we can then make the whole thing a bit more complicated, so that we can then add features like add something, remove something, create maybe also const iterators to demonstrate how those work. And we have 15 minutes, so we could actually implement a simple iterator already now. So we just go to our array where we already have iterators. We see what was it, begin and end, and then iterator. Let's copy the whole thing and then just adapt it so that it does what we want. So this will be an iterator. It will take an other. This is okay, but internally it will of course work differently. That will be C list, C list, per list. It does not have a index or anything. Just well, actually we can make it even better, even simpler. Let's see, maybe not better but simpler. We just start with entry and then just go through the whole thing until the entries are exhausted. Can even leave it at next. So next is equals per list head m head or just go with directly m as list then m. Okay, so this just goes with pnex data. This goes with reference of pnex data. Oops. Well, that's pretty. Just pnex, next, and that's it. Next, next. This makes a copy, and this advances it. So pnext is equals pnex next. This we just copy here. Oops. The assignment just assigns pnext. This just makes a copy. Then we of course need our begin and end. So begin starts with just m, and the end iterator is just null. Oops, no, it's like the simplest as it can be. Then we just need a test print for our thingy. So let's here let's go like this for const auto reference from my list. Space new line. Okay. Why is m0 null? Right. This of course needs to be m. Okay. Zack. 2 for 1 0. Nice. Okay, so the iterator was quite easy and simple to add. Then of course we could add here implement reverse iterator. So that we can iterate the other way around. And what else could be a good homework assignment? I mean, let's first make a list of what are all the functions that we want. Not everything for homework. Some of them will be for the next lecture so that you can implement them. It would be nice to have a find. Int find const reference const reference what? The find doesn't have any how to call it index, because there is no index in a list. It just looks for the whole list and finds the first occurrence of what it's looking for. We could of course make it like start searching from an input iterator, like iterator comma iterator so that we can kind of find the next occurrence and the next. That is quite useful. Then we could of course add a remove iterator erase iterator. And the way erase usually works is that when you erase an element, it will give you an iterator to the next element after the one that you have erased, so that if you would want to go through the list and erase everything, you could. Or if you would be iterating a list and erasing some entries and leaving some, so you basically iterate through a list, you check if an entry fulfills some criterion, and if it does, then you erase it. Then you would want to be able to continue a loop with the next element instead of being in a situation where you then need to restart from the beginning, which would be really bad. So for the performance, I mean. So this is why we would have such an erase. And of course, the next thing would be an insert. Insert. Yeah, what is okay? Where? Or let's call it the value. And the insert is similar. You give it an iterator that points to an element, and it then inserts something, and then gives an iterator that in this place, and then it gives you an iterator that points on the currently inserted element. Of course, then the next element you would iterate to by plus plus would be the element you had before at this place. So insert inserts always before the thing. One could also implement a function insert after, which would inserts after the element your iterator is pointing to. It's a small difference, but it's quite convenient to have both functions on hand. Yeah, but I think this we will be looking into during the next lecture for this homework assignment. Making the list work both ways is of course I think already enough. Plus we want to have some things that you can implement during the next lecture. As you see, the list is quite simple, so it has less options than an array. You don't have any square bracket operators, you don't have an add function, you don't have a mid or something like that. One could in principle create a function that emulates mid, and you just feed it two iterators, and then it takes whatever is between those iterators. But at this point, this is just manually going through the thing. So one, I think, could just implement it manually with append and so on. So we don't need a function that would do this directly. It's, I think, also not quite common to provide such a function for this sort of container. Yeah, and I guess that will be that for today. So I think last time we were a bit over time, so this time we will be a bit under time. Unless you have any questions. Okay, if there are no questions, then we'll see each other for the lecture in 3.5 hours, and yeah, and that's that. So let's stop the recording.